There we go. Does anyone have any questions about anything before we dive into 2.8? Okay. Oh boy. Oh boy. Okay. No questions? Well, then let's do it. So we're going to do two things today. First, we're going to go through how to determine what's the best type of model for a data set. In this course, we only talk about two models, the linear model or the exponential model. Those are the only two we study in here, but there are tons of other models out there. Just probably infinite. So don't think that these are the only two. And at the same time, the data sets that you are generating for your project are most likely not going to, neither of these models are going to be very good fits for them. Stock data is crazy chaotic. So you're not going to be able to, those things are not going to fit really a linear exponential, but you never know. Depending upon what you look at, it could. The budget one might fit one of these two. So you might have decent R values, but don't freak out if your models are terrible. All right. So we're going to determine which one's best, and then we're going to actually model that data, and then we're going to do some predictions. We've kind of already done this, but we're going to do it for real. So first things first, we are given a data set. And oh boy, I wish I could tell you what page we're on. This is 2.8, a little way through. And what we have here is the cost of attending college. The table here, just so we're clear on what the data set is, it is tuition and fees for four-year American colleges and universities. So this is not a 2-year, which is what we are. We're a 2-year university. So presumably our costs are cheaper than this. Now, you need to note something. Thank you, Janice. Page 239, everyone, is what page this is on, if you didn't notice the chat. Notice that we're told what X is. It's the year since 1980. So the next page, you don't have it written out like this. He didn't do that nicely for you. It's just this blank one. We're going to rewrite this stuff as X's and Y's. But I'm going to argue, let's not rewrite it. Let's just put it into Desmos, because that's exactly what we're going to do. So reminder of this in case you've forgotten. In Desmos, to put a table in, you put a plus, click the plus sign in the top left corner, click table, and type away. Now notice 1980 is our 0 value, because we're told we're looking at 1980 as the starting. So then 1990, like if we don't recognize that's 10 years, you can literally type into Desmos 1990 minus 1980, and you get the value for X that you need to use. So that would be 10. 2000 would be 20. 2010 would be 30. Ooh, and then 2011, that would be, oops, that would be 31. And then 2012 is 32, 13 is 33, 34, 35, 36, 37. Does that make sense to you all? How I got those X values? Maybe, you know what, maybe I should write it in here. What you can literally do is type in subtract 1980 from each of these. Why is that so bad? You can do this very thing in your projects, if that's how you're working with things. Although if you're going by days, I don't know if that works as well. Okay, so you should have that for your X values. You then just need to copy in the Y values. So I'll pause here and you all let me know when you've got this table copied into Desmos. All right, excellent. We got 3 out of 7. That's almost 50%. And I recognize some of you aren't able to do this either. So I'll move on. If I'm going too fast at any point, you all scream at me and we'll rehash whatever I've gone too fast on. So remember, if we want to see the scatter plot, you want to click the little zoom fit button in the bottom left. And there is the scatter plot of our data. Doesn't clearly look linear or exponential. I mean, if we just did these 3 points, that looks linear, or we just did this set of points, that looks linear. It also kind of has an exponential curvishness to it. Although this kind of curvature this way is a little strange. That's not exponential or linear, really. So if we go on to the next page, we did this already, forget that. Here you're going to guess what you think it is. You just write whatever you think it is, and then we're going to use our graphing calculator, in other words Desmos, to find, note he says, a linear equation of best fit. So you may, those of you that have done the worksheets and started your project, you know what to do, right? Y1 tilde mx1 plus b gets us the linear equation. And then our author says to round all coefficients so that they have 5 total digits. So I'm going to take this equation and I'm going to write it down here using this m and this b. I'm also going to use function notation because it's going to be helpful for later things. So I'm going to let the linear equation be called f of x. So 414.94x plus 574. And I'm actually, we'll do what he said, 0.80. That's our equation. That's our linear model. Has everyone got that? All right, awesome. So the cool thing is with Desmos, right, is we've already done this. And based on the graph, what do you think your model fits? Hey, it looks pretty good, right? The points do seem to be, like if I make this full screen, these points do seem to be pretty close. We already know about R. That's a really good R model. So looks good. We'll just say it looks good. Points are close to the line. And R is close to 1. And then he's like, hey, what's the correlation coefficient? And then does that mean the model fits well? Well, we already said that. So R here is approximately equal to 0.9915. You can ignore all of this stuff because Desmos Desmos does its thing for us automatically. And again, we already set it up here, right? It's close to 1. R is close to 1, so it's a good model. It's a really good model based on how close it is to 1. Now, does he ask us to do this? Yes. Someone tell me the number for the slope. Like, what is the slope in our model? Awesome, Janice, nailed it. 414.94. It's literally the M value, right? So we say, or the number times X, number times X. Now I'm going to be a little picky because it's technically 414 over 1, because what these things are, the x-axis is years after 1980, and the y-axis is college tuition. Let's just say tuition. Can I spell tuition? There we go. And this is in dollars, US dollars. So really what this is, if we're to put the units in, it's $414.94 per 1 year. So if we're going to interpret this, can you all write that sentence? Just like you're going to do in the project and on the worksheets and on the review and on the midterm. How would we state what this is? How would we turn this slope into a sentence? I'll get a refill my water bottle while y'all type it out. Oh no, they're not frozen yet. Oh no. All right, let's see what you got. Each year tuition is increasing by 414.94. Yes, I would. The only thing you should add is the year after 1980. Yep. Janice, I like that you added the y-intercept in there. You don't need to when interpreting a slope, but that's a good thing to, that's the next one we're going to do. So I will write that down. Let's see, tuition increases, because it's a positive number, by $414.94 per year after 1980. Or what are the things you said too? So I didn't copy exactly what you all said. Perfect. Does he ask us for the y-intercept? Yeah, so now let's do the y-intercept. Anyone know what the y-intercept is? It's the one that most students get slightly incorrect because they don't write the y-intercept down correctly. Hint, hint. Really stinking close, Jennifer. Don't forget the x coordinate. Yeah, Janice, nice. It's easy to forget that x coordinate because when we look at the equation, right, the b value is the y coordinate, the y-intercept. But ordered pair, a y-intercept is an ordered pair. And it's important to keep track of that, in my opinion, because 0 tells us the x value. So I'm just going to write this sentence down. In 1980, tuition, boy, am I spelling it right? Boy, I definitely didn't spell it right there. Tuition was $574.80. Well, tuition and fees. Notice that that doesn't at all match the data values, right? It's way below the data value in the data set. That's okay. One of the other mistakes students make when identifying the y-intercept from the model is they want to pick it from the table if the table has a y-intercept in it. You don't always have a 0 in your data value. In your project, you'll have a 0 in there because you're using time. So anytime your data set contains time, you pick a time 0, and that becomes your y-intercept. Cool. Okay. So now we're going to find the exponential model, unless there's any questions on that. Is everyone happy about that mess? Also, I'm going to just go ahead and type in our function for the linear model of 414.94x plus 574.80. Okay, so for the exponential model, we're going to type in that model we learned last time in 2.5. So since our table still has x1s and y1s in it, we're just going to do y1 tilde. And then the exponential model is AB to the x. Great question, Janice. That's the actual cost of tuition in 1980. The actual cost was $1,679. Models are always estimates of data values. And so this shows us that the initial value as predicted by the model is not very good. And that's almost always going to be true, that the y-intercept for the model is going to be different than the y-intercept for the data set. That's just how it happens. Okay, so one special thing with the exponential model. Let me make sure I label this. Exponential. You've got to click this log mode in order to get the R value. I also want to fix how I spelled tuition here. There we go. Wait, that does not seem. Let me make sure it bothers me that I'm spelling things wrong. Oh, I had it right the first time. What's wrong with me? Where did I spell it wrong here? Painful, painful. Okay, so you got to click that log mode. Man, why does that seem long? Whatever. I can do this, right? I can calm down. We got to click that log mode so we get the R value. If you want to know exactly what's going on, what the calculator is doing is it's taking log of both of these and then doing the linear regression. That way we can compare the R's directly and the R squareds directly. So let's do this. Let's write this down. I'm going to call this function g of x. And I'm going to write all of the stuff here. 1976.34 times 1.06173 to the x. That is our exponential model. I know I'm leaving in 1, 2, 3, 4, 5. Okay, fine. We'll delete the 3 like he asked us to. So then we only have 5 digits in there. There we go. And then we can see that thing graphed. Note, it fits the early data values a little bit better than the linear model. It's got a closer y-intercept, but these later data values, it doesn't really fit very well. And it's continuing up like this, whereas these values seem to be kind of a little more linear. So we've done that. We've got our graph going on. All right, so now we need to identify these two parameters. So let's start with the base of the exponential model. That's the b. That's called the factor. So in this case, our b is 1.0617. Since this number is larger than 1, we call it a growth factor. And we can calculate the growth rate by subtracting 1 from it. Y'all with me on that? Do you remember that from before? Maybe I didn't write this down. Maybe I'm confusing what we've done here with something else. In other words, it's a growth rate of 6.17%. Does that seem new to you all, or is that kind of what we've said before? I might be confusing what we've done online with what we've done in person. So how we would interpret this, there's two ways. One way we can say is tuition has grown by a factor of 1.0617 per year since 1980. Or, let's see, well, it's not going to let us do that. Or we could say tuition has grown by 6.17% per year since 1980. Either one, they mean exactly the same thing. Now, we can't say tuition has increased by 1.0617 per year since 1980 because that suggests addition. You have to use that word factor if you're going to talk about the B value. If you're going to talk about the percent, you can just write it in grown by this percent per year. Remember, and maybe this is the first time you're hearing this, this 6.17% is the percent change from year to year. In other words, that's the new minus old divided by old formula that we did back in chapter 1. Should be a minus in there. How are we doing, y'all? Is this seem okay, or is it crazy talk? It's okay. All right. That's probably okay and crazy all at once. Who knows? All right. Can anyone identify the y-intercept and interpret it in context? And I'll start. Y-intercept is 0, something. And I can't help myself. I'm just going to say it. The y-intercept is 0, a. So it's the 1976.34. So in the exponential model, it's the number times the base. This thing. And the interpretation here is the exact same interpretation we wrote back here. In 1980, tuition was blah, blah, blah. So in this case, for the exponential model, we're saying in 1980, tuition was $1976.34, which is a little bit better 1679 was the actual. It's a little bit better y-intercept than the linear model. But that doesn't necessarily make the exponential model the better model. What we need to look at is the correlation coefficient. So the correlation coefficient for the exponential model is R equals 0.991. That's close to 1. So it is a good model. Now the real question is which model is the better one, the linear or the exponential? Which I believe is what number 12 is asking us. So what do you all think? Which model is best? And more importantly, how did you know that that was the best model? Why do you all say linear?
Is it because if you're gonna round, it would actually be 99.2?
Love it. So I'll use some notation that might not be fun, but is kind of cool in the math world. So I'll do R subscript L for the linear correlation coefficient. That's 0.9915. And then I'll do R subscript E for exponential correlation coefficient. That's 0.991. Notice I'll put a 0 after it so they have the same amount of decimal places. As what you said in the chat, the coefficient, the correlation coefficient for the linear model is larger than the coefficient for the exponential model. Therefore, the linear model is best. Oh boy, what am I saying here? No worries, Janice. I knew exactly what you were saying. Oops. Erase. Yeah, so this is what you're going to be doing in your project. You're going to create both models. I'm just going to say this because of that statement. And you're going to say this model is better because such and thus. And really, you're just going to say the linear model is better because R is closer to 1, or the exponential model is better because R is closer to -1, depending upon whether your model is positive or negative, growth or decay. We have mostly looked at examples of growth, but it certainly could be the other direction, where the numbers are getting smaller as X gets larger. So just be mindful of that. All right. Well, let's do a prediction now. So we're going to predict, we're going to use both models, and we're going to make a prediction of the tuition for our current year. So the year we're going to predict is 2022. The question is, what should X be for our model? Now I'm gonna move this model down here so we remember it. That was the linear model. I'm gonna type in our exponential model real quick so they're right next to each other. And then we got to decide what's X gonna be. Oh, how would you get 42? Nailed it. Yep. So our table of values and the functions we've made from these table of values, these models, have X being the number of years after 1980. So if we're predicting a value now in a new year, we take 2022, we subtract from it 1980, and we get that nice number of 42 years have passed from this first data value to our current data value. So to do the predictions, since I've typed in the functions as they are, f of x is the linear prediction and g of x is the exponential prediction. So here's our two numbers. The linear model predicts the tuition to be $18,002.28. And the exponential model predicts it to be $24,430.82. Those are our two predictions. Now we're supposed to go calculate these things. Yeah, not a problem. So for this linear function, what I did is I took this equation or this model that Desmos gave us, and instead of writing y equals, I wrote f of x equals, and then I took the m, which is the 414.94, times the x plus the b, 574 point, and then I rounded to 2 decimal places, 0.80. So there's where the linear one came from. I just took the parameters that Desmos gave us for m and b, and I replaced y1 and x1 with f of x and x. And you should always do that when you're working with these things, because this is code to find the model, and then you want to type the model into Desmos like I did here, so that you can then work with it, like do calculations and such. And then I did the same thing for the g of x function, or the exponential function. I just replaced y with the function notation, g of x, and I used these two parameters and wrote them exactly how they're stated to be written right here. So the a value is 1976.34. The b value is 1.0617. We were told to just have 5 digits here, so I ignored the 3, and there's my function. Is that help? Okay, good. Because then what was so nice about using that function notation is then I could just write f of 42, there's my answer, g of 42, there's my answer, done, 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 right? So our author then says we are to find the error in each prediction and the relative error, or percent error. So we need to go figure out what is the actual value. Let's see. So let's Google 2022 tuition and fees average 4-year college. Okay, here we go. 4-year the 20 fees for state residents, for out of state, for graduate programs. Okay, here it is. Oh wait, man, what is the average? So we'll use this number. It's crazy off. $4,801 per year is what we're told is the actual data value based on this website. You all see what I'm looking at here? What is our source? xpcourse.com, average college tuition. Does that seem like a decent source? Maybe let's use this one. The source doesn't seem that much better, but the number is closer to our predicted values. And they're all kind of, if you notice all these different spots, they're all kind of close to this 9,000, 8,000. This one says the average tuition for 4-year public institutions is this for in-state and this for out-of-state. All right. We just got to pick one. How about we use Wesleyan University? They seem like a reputable source. 9,085. We're going to claim that's the actual value. All right, so I'm going to go back to Desmos, and I'll put that in a note, and I'll say the actual average tuition for 2022 is $9,085. As you know, based on that source. So error is defined as actual minus estimate. Is that how we've defined it? Does that seem like we've done what we've done? So the actual value minus the estimated value. Now notice what I'm doing. I'm just typing in f of 42. So for the linear, error for the linear, that's negative $8,917.28. And then I'll do the same thing, 9085 minus G of 42. And that is, woo, the error for the exponential. Okay, this is getting way too confusing, my notation here. I'm just going to write out the words. Linear error is that. Exponential error is this, and it is the, ooh, way off, $15,345.82. If we subtracted the other way, those numbers would just be positive. What this is saying is that the model, the predicted value is above the actual value by that amount. We'll just say so then the relative error is just these things divided by the, so it'd be the 9085 minus f of 42 and all that divided by f of 42. And remember, the relative error here is really the percent error. So the linear relative error is approximately equal to negative 0.4953 or 49.53% above the actual value. And then the exponential relative error is approximately equal to negative 0.6281. In other words, 62.81% above the actual value. So this is a nice way to see that our R values were correct, that the linear model is slightly better, although they're both pretty awful. And I think one of the things that could account for this actually is COVID and what the federal government has done with tuition dollars. Like they've given students lots of money, probably not enough, but have I don't know if you all got any like refunds from Jackson College, COVID dollar refunds. When I was going to Eastern last semester, last 2 years I was at Eastern finishing a degree, and Eastern sent me tuition, like COVID assistance money. And I'm wondering if that has anything to do with these smaller numbers. We could look at, like, what was it for 2018, the average tuition dollar costs, and nope, it's still about the same. So You know, that's probably a wrong thing. We'd have to really look around and see why did these numbers not match what our model is suggesting, even though our models are, and because our models are really good model. Let me pause here and make sure everyone's comfortable with how I typed these things in here. If you don't like this function notation, you can type in this 1802. You can type in that value and you get the same thing. To me, it's nice to have this, to use this function notation because it's less writing. And in some ways, I think it's nice to see that, oh, whatever you're subtracting, you're dividing by. So you know that these match up with that relative error formula, or percent error formula is another way to look at it. So does anyone have any questions about what you've seen here? Yeah, it's strange. It's the direction we did the subtraction, right? Because we did, how we subtracted these numbers is we did estimate minus actual. So because the estimate is a larger value, when we subtract the actual value from it, we're going to get a negative number. If we flip these around, if we did actual minus estimate, so that would be like f of 42 minus 9085, you get a positive number. G of 42 minus 9085. And that's why the formula doesn't actually matter what direction you do it. You get the same results when you interpret it. So here this says, oh, look, the estimate is this much above the actual. So when it comes to exams, like if you do flip the order around, as long as you interpret it correctly, you're good. By the way, the relative error, we'd have to be careful here. The numbers aren't just positive, because now it's the percentages are not just the positive values, they're a little bit different. But these percentages mean the same thing. Good question. Did that help at all, Janice, or is that still like just crazy talk? Okay, good. So there is one other thing that sometimes people do when they look at this. If you look at the 1980, 1990, and 2000 data values, those are these values right here. And they seem to have a different pattern than the more recent data values. These are year by year. These are 10 years apart for each. So the author says, well, why don't we take those out? And let's start with the year 2001 as our starting value. So what we would do is delete all these values. All right, so they're gone. And then we would redo these as 0, 1, ooh, stop that, 0, 1, 2, 3, 4, 5, 6, and 7. All right. So we now have a new data set. It's really the same data set, but we've shifted the y-intercept to have a year starting in what is the starting year? 2001. Now, because I left everything in here, these are the new models. I need to hide these because these are no longer valid, these two function models. In fact, we're going to want to rewrite them in a second. which we will, and then it'll redo all the calculations for us. And so here's the new look. And if we look at the linear, if we look at the R values, 0.9895, 0.9852, the linear model is still slightly better. Notice our function, our parameters are a little bit different now. So let's write those down and then just see what happens with our predictions. So I'm going to come over here and I'm going to write them in here, the two new function models. I'm still going to use f of x because it will just automatically change everything we've written down below. We're doing 412.85x plus 13,169.40. Notice that y-intercept, that's not too far off from the actual y-intercept. And then I'm going to write down the exponential function here, g of x equals 13,195.8. Oh, those two are really close together, times 1.028. I'm going to leave all the decimals in there for that, 9x. So what I'm going to do now is I'm going to rewrite these things with their new numbers, and it will change everything because it's all tied together. And then we don't have to recalculate the error, and we can see if we get a better error, a better difference between the two. Okay. Oh man, I think that got worse, didn't it? These percentages went to 70% and 79%. So that was not helpful at all. Oh wait, yeah, it wasn't. It wasn't at all, because it made our predicted values much larger. Oh no, I've got the wrong number here for 42. My bad. We need 2020 minus 2001, and that will get our predictions a little better. All right. Let's see, what is that, 19, right? So I can just put these in here as 19. No wonder it was so bad, right? This should be f of 19. It's still not a whole lot better, is it? In fact, it's is it better? Let's see. It's a little better, right? Let's go back to where we looked at those percentages. It was, nope, it's worse. The linear model is a little bit worse. And actually the exponential model in terms of the amount of error is a little bit better, because it's 59.97 versus the 62.81. But looking at the R values, the linear model is still the better model between the two. Okay, I did a lot there really fast. It suddenly occurs to me. Did you all follow what I did here? Like, it might be helpful me to recap. I deleted the first three data values and created a new starting value, a new year 0, and that year 0 corresponded to 2001. I then allowed Desmos to find the new models, which it did automatically because I just changed the data. And I wrote down the new functions in here, because I could graph them again. And then I recalculated the number of years between our starting year, 2001, and our current year, 2020. And we checked our predictions, and they were worse this time around, except the exponential model was slightly better, 59% percent error versus 62% error. So in your project, let's see if I can find the project. This is pretty much exactly what you're doing. Oh, this is an old project. Here we go. So for the first task, you've compiled all this data, and then you're finding that linear model and that exponential model, and you're either screenshotting. Remember, you can actually just do what I've done here in Desmos, and you can type it all up and put your notes in here, and you can just save this graph and send me the link, and I'm super happy for that. You're then stating which model is the best fit, and you're going to explain based off the graph and the correlation coefficient. You're going to interpret the parameters of the best fit model. And then you're going to predict a stock value in the future based off of your model. So you just, whatever your prediction, just predict a couple days in the future if you're going based off of days. How you do this doesn't particularly matter. Just clearly label what your X is. So what prediction are you making and how did you get it? And then for the federal outlays, you're doing, in this case, you're doing the difference, or we could also call this the error, after you make that prediction. And so for this one, you're predicting the value for 2019. And notice I said use a randomly generated year assigned to you for your starting year. Just pick a year between 1962 and 1970 and you'll be fine. Any year between there, and then you're picking any category on that you want, any line item in that Google spreadsheet, and you're generating those 10 data values. Again, you're creating a model of best fit and how you know which one. You're identifying the parameters and interpreting them, and then you're predicting that amount. So for example here, if 1962 is your starting value, your X is going to equal 2019 minus 1962. That's what you would do there, and then calculate that value, whatever that is. And then do this relative error and relative change. And you can do it exactly how I set it up here, where you type in the function notation. This is the difference or the error, and then this is the relative. And showing your work, if you just give me this Desmos file, that is your work. For example, I guess I could have done this for you all. I've clicked this share graph, I'm copying, and then you could submit, you could give me that link, upload that link to Canvas, and then I've got it. If you all click that link that I just shared with you, you get all of this that I just put together. What questions you'll have?
Are there supposed to be 4 tasks for the Unit 2 project? Because you only have 3 posted.
Good, there should only be 3. I wonder if I posted the wrong one. I think we got rid of this. Oh yeah, this is an old one. Ignore this. This is what? Because your third task is different than this. Your third task is based off of your what you did in Unit 1 project, that ibuprofen stuff, right? Let me just go to Canvas and pull it up. Thank you for mentioning that. Oh, I can't log in. I don't have my phone. Yes, it should only be 3 tasks, and your third task is different than what you saw there. And I think the write-up for things is a little bit different than what you saw on my screen too. Maybe not. Okay, then the other thing we should talk about is the course pack, the worksheets that you should be turning in. I think the due dates are messed up a little bit. You know, my deadlines are all just get them done kind of thing. But you should now be ready to turn in all of the worksheets or complete them all. So 2.5 and 2.6 and 2.8. I don't think there's a 2.7. There's a 2.5. Man, there's your 2.6. There we go. And there's your 2.8. Oh, definitely. Yes. Let's do the 2.8 lesson check too before we forget. And then actually what I want to do is, oh, I can't log. Okay, let me just get logged in here. I have to be able to get logged in. I'll be right back. Thank you, Jennifer, letting me do that thing. Yeah, let's do all that, y'all. Let's work through stuff. First, let's do the 2.8 lesson check to make sure we all know the answer to that. I believe it's the R value for one of them. Sometimes I really hate Canvas. Okay, so here comes 2.8. What's the worksheet? Curse words. There's a lesson check. All right. Yeah, it was the correlation coefficient, question 11. So let's make sure we got that one right. So 0.991, but let's see, I think, does it say to round to a particular decimal place? Round to 2 decimal places, so 0.99. Whew, okay, 0.99 is what that should be. Let me make it unlimited for those of you that got it wrong. Oh my goodness, come on. Allow multiple attempts. Well, that one's good. It's 130i. While we're here, I'm going to quick download this. Oh, they're both multiple attempts. So if you got it wrong, you can keep attempting till you get it right. Just so we're all clear on the this is what the third task looks like. So you're using your information from project 1 to create a table of values and do some modeling here. So let's take a look at the 2.6 worksheet for starters. And I was going to write this stuff up for everyone anyways. So let me just do number 1 with you, because I was going to write I was going to summarize all of this into one nice, beautiful thing. So the general form of a linear equation looks like this: f of x equals mx plus b. The parameters of that thing are m, which is the slope, which is really the change in the y variable divided by the change in the x variable, and you need that for interpretation. And the b is really the y-intercept. Oh, let me write it that way. So it's the y-intercept, which is 0, b. And then the two basic shapes of the line are this. Shoop, that's a positive slope. And shoop, that's a negative slope. If we are finding the model, in Desmos, we do y1 tilde mx1 plus b. Although those x1s and y1s could be different numbers, it's based on whatever's in your table. And then from that, we get this correlation coefficient called R. And any number, let's see, close to 1 or -1 is a good fit. So that's like everything linear. Maybe you prefer not function notation, which is okay. That's equals y equals mx plus b. I think it's important. I shouldn't say I think. I know it's important to make a distinction between what you have here and what you have here, right? This is to find a model. It's a regression model or a line of best fit. Whereas this is the equation you've written down. This is the model with the numbers in it. So when you type stuff into Desmos with the equation, you should have a number here and a number here. Whereas when you type this in Desmos with the table, it's going to find you the numbers you're going to use. Oftentimes I tell you to round these things to a particular set of digits. Any questions on that linear stuff? Oh, I should also mention there are other forms of equations, of lines, linear equations, that we don't talk about. There's standard form, there's point slope form. We don't mess with those. So don't worry about them if you know about them. So there are also other graphs of lines, right? There's the vertical and the horizontal. Again, I don't think we're going to encounter any of those models. So the exponential model, I'll use g of x, although it doesn't matter. You could use f of x again. That's this. This is a times b to the x thing. And its parameters are a bit more complicated. So if b is a number larger than 1, we call it a growth factor. If b is between 0 and 1, we call it a decay factor. And then if we want to find the rate, so that's the percent growth or percent decay, I'm just going to say rate here because it's this one if this number is negative, or it's this one if it's positive. This rate is equal to, let me get it right, b minus 1. So that's the percent change. That's another way to think of it. percent change. So when you do that subtraction of 1, if you get a positive number, you know it's a growth rate or percent growth. And if you do the subtraction, you get a negative number, you know it's percent decay, or percent decrease is another form for that. And then from this, the other option, the other parameter is the y-intercept. Exact same interpretation as linear, we just use a different letter, 0, comma a, and that's the number times the base raised to the x power. Like the linear thing, the model we use, or the code we use to find the model in Desmos is y1 tilde ab to the x1. And same thing, we have an R value that's the correlation coefficient, same interpretation. The one exception here, the one thing you have to keep track of is you've got to check this log mode box so that you can get the R value. So I'll just do that and I'll put R. C linear. There are 2 graphs. This is the growth shape of the graph for b greater than 1. And this is the decay shape of the graph for b between 0 and 1. And that's really everything you need to know for the exponential models. I guess the one other thing you need to know, if you have to solve for x, you're going to graph g of x, and then you're going to graph y equals some number, and what you'll see is something like this, and the solution is where they cross. It's the x coordinate. This is the solution. And we did that back in 2.6, but that's and that will happen to you. Any questions on this mess? This should go on your reference sheet for the midterm. And in terms of the midterm, what we're going to do is review for the midterm on Wednesday, and then you will take the midterm by, I guess we'll say Monday. I'm going to put it in Respondus. We'll talk about that on Wednesday. That I got to set up that quiz so you can practice. And what happens is you'll have a video recording of you taking the midterm by Respondus, and you'll be able to take it anytime you want within a particular time frame. Okay, how you all on number 3? Do you think you can do that problem? You want to try it? Let me mention, while you're thinking about it, let me mention a couple things. This is vague. Find a regression equation that best models the data, is what that should say. So you have only 2 options from what you learned in this class. It's either linear or exponential. So you do exactly what we did in class today. You type this data set into Desmos, you write in put your codes in for linear and exponential, and you see which one is best based on the correlation coefficient, which number is closer to 1. Don't try to put these percentages in Desmos. It won't understand that. Just put in the numbers. So how about I give you like 10 minutes to try this problem, and then we can check how you did. If that sounds good to you all. And by the way, if you can do this problem, you can do all of the rest, because this is the same thing. Put the data in, figure out a regression equation that best models the data, say some stuff about it. Put the data in, find both models, pick which one's best, predict a value, right? So it's the same stuff we've just doing. So if you can do one, you should be able to do all, because they're all basically the same. It's just, it could get tricky based on, are you talking about Are you interpreting the M and the B, or are you interpreting the A and the B? So let me set a timer for 10 minutes, and then so that you can try it. And then if you want me to go over the solution, we can go over the solution. If you're like, no, I just want to go do this on my own, that's fine too. Here we go. No, pause the reading. No, I'm not going to pause the recording because then it makes a separate video. All right, have at it, y'all. If you get stuck, ask me. Well, so in the exponential function, the A value corresponds to the y-intercept. The B value is the growth or decay factor. So there is no slope. That's like the equivalent to slope in the linear model. It's the change. So if you remember what happens in linear models, the change is constant addition. So slope is being added X amount of times, right? And then in the exponential model, it's constant multiplication. That's like the identifier of how we know something is growing exponentially. So the B value is the factor that's being multiplied X amount of times. So you wouldn't call any of the parameters in the exponential model a slope model, if that makes sense. It's just either a growth or decay factor. So you would be thinking about that B value in the exponential function as one of these two things, this thing or this thing. Whereas in the linear model, this number here is only one thing. It's the slope. And either it's going up or it's going down. Does that make sense? It's a good question. Excellent, excellent.
So in Desmos, how are we getting the exponential and linear graphs? Like, how are we getting that in Desmos?
Did you type in your data set like this?
Yes.
And then did you type this in exactly where this Y1 and X1 match what it says here?
No.
So that's what you have to do. You got to type these two things in exactly how you see it. That tilde button, which is like a rarely used one. This is the first time I've ever used it, honestly. You can find it here, or it's shift the button above tab. That's what this little thing is. And it's literally just it's just the code you're typing in. Think of it as like coding. You're saying, Desmos, go find this thing for me. So that was 10 minutes. I don't know, we've had a few questions here. Do y'all have any more questions about how to get this? Did anyone get the answer for A? Nice, Janice. Yeah. Oops. Why is the exponential the better model? Oh, that was that garbage. So this is the one you want to write down. G of X equals. Nailed it. Yep, that's all you're doing is you're comparing the 0.9948 versus the 0.9989. So the exponential model, which is 4.78 times 1.03 to the X value, its R value that's approximately equal to 0.999 is greater than the R value of 0.995. So this is the exponential, this is the linear. Yep, that's the closer one to 1. Good. So that's the model you should be using. From here on out, are you all good with how to do the y-intercept and the exponential and the growth factor? By the way, because we've identified that it's exponential, none of this other stuff matters, right? This is all, nope, it's not linear. So we're not going to talk about the slope. Yeah, definitely. So first, excuse me. The first thing you should track is anytime we're talking about a y-intercept, it needs to be written as 0, comma something. That's the y-intercept. So for the exponential model, it's always the number times the thing being raised to the exponent. That's called the base. So the b to the x. So in this case, it's the a value. And that's kind of what's nice about Desmos is it separates the two parameters. Like you don't have to look at the equation and say, well, which of these two numbers is a? We just have it identified here. So in this case, it's the 4.78. Now the context here, we have to read the prompt or look at the table. This is years since 1970, because we did 0, 10, 20, 30, and 40. And the Y value is the percent of the US population that is foreign born. So what this number is, it's in 1970, and maybe this would help our interpretation. We could say the model predicts that 4.78% of the US population is foreign born. Does that make sense, y'all? I get that it's not the same number as the table, right? The table says 4.7. That's the actual value, but this is what our model is predicting it would be, and it's not too far off in this case. So it's not a terrible prediction. If you look at the linear prediction, it's 4.34, which is a little worse. But it's not too bad. Is that helpful, you all, or is it? You think you can do that when you do the project? Excellent. Okay. How'd you all do for B or for C? How did you interpret the growth factor? Just while we're here, the growth factor based on what we wrote down above is B equals 1.03. What did you all say for that interpretation? Or did you have no clue, which is fine too? Well, there's a typo here. This should really be 2017, or these two should match. No clue. Love it. That's okay. So what you're going to do is the exact same thing we did here. Let me save this. Worksheet. You're going to do this. Whatever it is, you're either going to say it's grown by a factor of whatever the factor was, or you're going to say whatever it is we're talking about has grown by this percentage per year since our beginning time. So these sentence structures you can use over and over and over. They always work in terms of the factor, and you either say grow or decayed by, or whichever is appropriate. So we just need to know what's the context. We have it here. It's years after 1970, and it's percent of the US population that is foreign born. So this is that context right here. So I would say that, so what we could say is the percent of US population that is foreign, now I'm spelling it wrong, foreign born, has grown by a factor of, oh man, grown. What's going on with my brain? Love it. US population after 1970 has grown by a factor of 1.03 foreign born. The one thing you need to keep in there, Janice, is that it is a percent. That's kind of important. because it's not amount of people, it's percentage of total people in the US has grown. So that's the only thing you should add in there. Because foreign-born has grown. I'll put in the rate by 3% per year. So this is the other one that you could write. Janus's is perfectly fine too, since 1970, when you include the percentage. How y'all feel about that? Is that feeling okay? And if this had been amount of people that were foreign born, which if we know the total US population, we could easily calculate that from what we know from unit 1. It's just not how the data is given to us. We could have said that. So you can either use the rate, the growth rate. Great question. Where did that 3% come from? Remember, the rate is equal to B minus 1. Been converted to a percent. And where that's coming from is what I wrote right here. This thing. Come on. That thing. So when you interpret the B value, you can either use the factor or the rate. I think in many cases, talking about the percent growth makes more sense. That's what you did already in unit 1. But either one's fine. You just have to make sure you use the word factor. Now notice you all, I fixed a typo here. This says predict the thing. Yours says 2016, but then down here I gave you a 2017 number. So you really need to do the prediction for 2017. Do you all know what to do with that? Or do you know how to do that? Okay, nice. So for those of you that aren't feeling so good, you've got to use this model and plug in whatever this X value is. So if you think back to what we did up here, we're saying, really it's T, not X, whatever. We're saying that the beginning value for 0 is 1970. So we have to figure out how many years have passed from 1970 to 2017 to get the correct number to put in for X. We're doing the exact same thing we just did in the textbook, which was where we predicted the value in 2022, which if we started in 2001 was 19. If we started in whatever the original day was 42. So we're doing this exactly. So what you have to do is you actually have to type in the equation you found. Which one was it? It was this exponential. Am I in the right? Oh, I didn't save. Lovely. So I'm typing in this g of x equals 4.78 times 1.03 raised to the x power. And then I can just type in here g of 2017 minus 1970, and it gets it for me. So if you like that function notation, which I do, you could just say, this is what I put in Desmos. And this is the result I got, 19.18%. So our model predicts that the percent of foreign born, the percent of the US population that's foreign born in 2017 should be 19.18. Well, then I went out to pewresearch.com and I found that it was 13.6. Calculate that relative error or percent error from our answer here. So this is the actual amount. That's the actual. And then this is the predicted amount. Again, that's the exact same thing we did in the textbook right here. This is the relative error one. I'm forgetting what we did in the book. Did we do actual minus estimate divided by estimate, or did we do estimate minus actual divided by actual? I think it was this one, wasn't it? Estimate minus actual divided by actual. Or was it the other way around? I can never remember. It doesn't actually matter which one it is, but it was way back in number 1, unit 1. How y'all doing? Is that making sense? So it's 27.5% off. If we did it this way, it's 27.5% above the actual. If you did it actual minus estimate divided by estimate, you'd probably have a slightly different number. And that, so what you just did here is exactly what the project is, like essentially 3 times. And it's exactly what the rest of these questions are. Find the model, make a prediction, talk to me about a state, interpret the parameters, the slope and the y-intercept, or the growth factor / decay factor in the y-intercept. Make a prediction. How far off is it? That's this entire unit. You're just doing that over and over and over until hopefully it just becomes second nature. And then you'll never ever use it again, unfortunately. It's not a very, this is not a very common thing that happens in real life. Unless you go into actuary or other cool things. Let's see. So let me do a calculation for it. Man, I keep not saving it. What's wrong with me? So we're gonna do the 2 different excuse me, the 2 different answers we could get for this last question. If we do estimate minus actual, that'd be 19.18 minus 13.6 divided by 13.6. There's the 41.02 blah blah blah. Well, we could do 13.6 minus 19.18 divided by 19.18. Either one of those would be correct. So both of those are slightly different than yours, Janice. Did I do something wrong, or did you use 2017 or did you use 2016 in there? Either one of these numbers is correct for this question E. Oops, there we go. No worries. So if you did it estimate minus actual, you'd get this 41%. If you do actual minus estimate divided by estimate, oh, come on. Divided by estimate, you get this negative 29.1%. Yeah, no worries. You're so good. I know that life. I'm listening to my daughters run around. So far they're okay, but you know, when the screams start, you got to go check what's going on. Or when they hit a certain level. They've been really good today. I've been impressed. I think they got good sleep last night. Cool. Do you all want to attempt the next problem? And then we go over it, or are you happy and think you can do it yourselves and think you can do your projects? Where are you all at? Like, what do you need from me? All right, let's do it. This first one, these numbers are ridiculous, right? They're huge numbers. That's why I said, let's write these in billions. So we're going to round them all. And that's what B says. We're going to rewrite the debt in terms of billions. I'll do the first one. This is the billion number. So we'd rewrite this as 257. all you have to do is keep track of this number right here. Like, is that larger than 5? If not, you're just writing the first 3 digits. And so none of them are, so you just rewrite all of them like that. And then you're off to the races. So I'll set the timer for 5 minutes, or we'll do 10 minutes, and I'll let you try this. I don't want to like make you think one way or the other. So no longer use this, use this. Be careful how you fill in this stuff. I don't even know. I don't even think I can do these. Oh, well, this is 17. Oh, that's 34. Oh, that's 48. I guess I can do that. These last two I'd have to type in. And then notice it says a regression equation that best models the data. So again, linear or exponential, either one, you decide based on R. Get it right, or you get all the rest of the stuff wrong. All right, well, I'll set that timer for 10 minutes, and then we'll look over what we've got. Do I not have a timer anymore? Good, 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 good. Who's that cool time? Oh, well. Because you're using billions, yes, this is what it ends up looking like. And then you're going to use this. This will be your X column, the T's. So this is X. This is X, and this will be your Y. Let's see, what does it say about rounding on the worksheet? It says round to 2 decimal places. The only reason I ask people to round to a particular set of decimal places for these equations is so that when I grade and you make the prediction, we all have the exact same prediction. Just saves me time. Because based on your rounding, it's going to change what your prediction is. Oh, that was 10 minutes. Y'all ready to talk about it? Did y'all get linear or exponential as the best model? Exponential, yes, because 0.9861, this R value for the exponential model is better than 0.8813. Good. So did you all write down, let's see, I'm going to write it this way. F of x, you can use g of x, f of x, or y, whichever one you want. It says 2 decimals. So that would be 188.38 for the A value and 1.071 to the X for the B value. Is that what you all wrote? So the parameters, do y'all know what parameters you're having to identify? Yeah, it feels like I can count, Jennifer. You're right. It should be 1.7. Yes. Because that's 2 decimal places. Yikes. Good catch. I will write the parameters. I'll leave the sentences to you. There's a y-intercept you have to identify. That's this. And there's a growth factor you have to identify. That's this. Which, if you want it as a rate, that's this. So your job is to write that sentence. Notice this is debt in years since 1950. So your sentences should include the fact that we're talking about total debt. It's actually, if you want to be super precise, here's the exact thing. It's the US historical debt outstanding. So it is a cumulative amount. It's what hasn't been paid from all years ever. Oops. And so you should have something about in 1950, it was this, and then it grew by this much since 1950. By the way, notice the numbers are in billions of dollars. So this 188.38 is $188.38 billion. Cool. How did you do with the prediction? Did anyone get that prediction? That's what I got. We could check too where we are on that debt. US debt clock. There it is. Real time. Predicted to be at 30,000. Oh, we're already past it in 2022. So we've passed the prediction. By $1,000 billion already. Ooh, not scary at all. Okay, questions? How'd y'all do? Can you do the same thing on this one? Nice, Janice. Good. Go crush that project. This is all the project is this stuff. In fact, probably if you get this process that we just did, the most confusing part of the projects might be putting the data together. And if that happens, let me know. I'd be happy to help you put that data together. Good luck. Treats, throw treats at them. Oh no, they're sick. You don't want to do that. How about Caitlin, Jennifer? Yeah. Children are Pandora's box. How about the rest of you? Anyone? How are you all feeling? Anything you're stuck on with all this? Any questions you have? You feeling like you can do it? Awesome, Caitlin. Okay, then I am going to stop here.